When we look at the leading term of a rational function, one of three things can happen. For example, we could have, let's say, x squared plus 1 over x cubed minus 2. Notice that in this case, the degrees of the leading terms are different and that it's bigger on the bottom. So we can have a larger exponent down here versus up here. Something else that can happen is we could have maybe a larger exponent. What if it's the other way around, where it's x cubed minus 2 over x squared plus 1 as our rational function? Notice that this time we have a larger exponent for our leading term in the numerator versus a smaller in the denominator. So this time it's bigger on the top. Another option could be that they're exactly the same. We could have, for example, x cubed minus 2 over x cubed plus 5. In each of these cases, and this case the exponents are exactly the same, in each of these cases there's something that we can notice. Let's say we took the first one and we wanted to know the end behavior. Basically, we are trying to figure out what happens as x goes to infinity or as x goes to negative infinity. Well, think about it. If we were to put, let's say, 1,000,000 here, and we squared 1,000,000, we get a very large number. And if we added 1 to that, would that plus 1 really matter to what that number is? Probably not. Similarly, if we put that same number here and cubed it, which we would have to because we can't put two different numbers here at the same time, we'd have to put the same. If we cubed it, what would happen? Well, that minus 2 probably wouldn't make that much of a difference. So if we're thinking about the end behavior, then really we're just thinking about x squared over x cubed. If we simplified this by dividing both the numerator and denominator by x squared, we end up with 1 over x. So this is going to describe the end behavior of what's really happening with our function. So think about it. If you put a larger value of x, you kept making x larger and larger, what would happen as this function kept getting larger and larger? Well, if I put in 1 over 10, then 1 over 10 is pretty small, 0.1. If I put in 1 over 100, let's say I put 100 as my x value, then that's even smaller. If I put in 1,000 for my x value, you can see that it's going to continue to get smaller. So basically, as x goes to infinity, as we get a larger and larger x value, the whole fraction or the whole value here becomes smaller. But will it be negative? If I keep putting larger and larger values, so for example, if I did 1 over 1,000,000, would I end up with a negative number? Or what about 1 over a trillion? No matter what I end up with, this value is always greater than 0. So basically, as x goes to infinity, our function value gets closer and closer to 0, but it doesn't go under 0. The same thing would happen if we went to negative infinity. The only difference is that we'd have negative numbers. So for our end behavior, we basically said that our end behavior would be represented by an asymptote where our function value gets closer and closer to 0. We call this the horizontal asymptote. So similarly, if we use the same kind of reasoning, this whole function here, when we get out to 1,000,000, is really the same as x cubed, or almost the same as x cubed over x squared, which is basically just x. So think about it. As x goes to infinity, is there anything that's going to limit it? So if I put 1 here, or if I put 10, or if I put 100, or if I put 1000, if I kept going for x, will x be limited by any number? No. If I keep putting larger and larger values of x, my function values will always be getting larger and larger. Similarly, as x goes to negative infinity, our function also will go to negative infinity. And we'll see what this looks like as a graph in a little bit. So in this case, there is nothing that limits it. So what we would say in this case is that there is no horizontal asymptote. What about the third example? So if we were to take this third example, when we get out to 1,000,000, that -2 and the +5 won't really make that much of a difference. We're basically dealing with x cubed divided by x cubed. And what is this equal to? Well, basically it's just 1. So we're just taking the coefficients and dividing them, and we're ending up with 1. So what happens is as we get larger and larger values of x, so if I put in 1,000,000 here and 1,000,000 here, 1,000,000 divided by 1,000,000 is 1. So similarly, if I put in 1,000,000 here, cubed it, and then subtracted 2, and then I put 1,000,000, cubed it, and added 5, remember the +5 and the -2 won't really make that much of a difference. The number that I get when I divide is going to be very close to 1. So no matter what value I put in for x, I'm going to keep getting closer and closer to 1. So what that means is that as x goes to infinity, my function values will keep getting closer and closer to 1. And as x goes to negative infinity, my function values will keep getting closer and closer to 1 also. Remember that the only difference is that this would be a negative up here, this would be a negative down here, and a negative divided by a negative is still a positive. So no matter which way you look at it, we're going to be approaching +1. So what we can say then is our horizontal asymptote would be the function y equals 1. Remember that in this case, we found out that when we looked at the leading terms, that concerning the exponents, they were bigger on the bottom. And so we said that y equals 0 was our horizontal asymptote. So here's y equals 0 right here, this blue line. And as we follow that blue line, we'll notice something about what the graph is doing. So the graph, as we go further and further this way, so as x goes towards infinity, so as we go to the right, look at what's happening with the graph. As we go to the right on the graph, our function is getting closer and closer and closer to 0. It keeps getting closer to that 0 line. So our function values get closer to 0 as our x goes to infinity. Also, if we went the other direction, as x goes to negative infinity, so basically when we go towards the left, what's happening to the function? Well, if we follow the function towards the left, then it looks like our function is still getting closer and closer to that 0. So what we can say then is as x goes to negative infinity, or to the left, our function is also going towards 0. For this reason, we said that, again, bigger on bottom, that we knew that y equals 0 is our horizontal asymptote. So as long as we look at the leading terms and we look at the powers on the leading terms, if that power is bigger on the bottom, then we know for sure that y equals 0 will be our horizontal asymptote, no matter which rational function we have. In this case, when we look at our rational function, this is the graph that we would end up with. So what happens as x goes to infinity? In other words, as we go to the right of the function. So as we go this way, if we follow the graph, no matter where we start, as we go further and further to the right, looks like our function value keeps going up. So in other words, our function value continues on to infinity. And as we go to the left, in other words, as x goes to negative infinity, what's happening to our function? Well, as we go left, our function is getting smaller and smaller and smaller. It's going towards negative infinity. So there is no line that limits it like in the first example. In this case, we say that there is no vertical asymptote. Sorry, horizontal asymptote. So asymptotes, horizontal asymptotes, represent the end behavior of the function. So if we have, as we said before, if we look at the leading terms on each of our numerator and denominator, and we determine that the power is bigger on the top, then we can say there is no horizontal asymptote. In looking at our third example, where the exponents are the same, they're both 3. So we have an exponent of 3 here and an exponent of 3 here. The exponents are the same. Notice what happens. If we follow our function towards the right, so as x goes towards infinity, what happens to our function? Well, notice that our function keeps getting closer and closer. And even though it looks like it's on the line, if we zoomed in a little bit more, we would see that it's just getting very, very close to that line. So it looks like our function value is getting very, very close to 1. Notice that this is 1 right here. So we're getting very close to 1 as we go towards the right. And as we go towards the left, in other words, as x goes to negative infinity, well, what happens to the function then? So if we go towards the left, notice that what happens is that we're getting very, very close to 1 as well. So our function value gets very close to 1 the further left we go. In other words, we'll say that we would have a horizontal asymptote through the line y equals, or at the line y equals 1. So what we can say then is that if our exponents are the same, then we will have to divide the coefficients. In other words, if there's a 1 here and a 1 here, we divide them and we get 1 for our horizontal asymptote like we have here. So to sum it up, we can remember that there are 3 cases or 3 possibilities when we're trying to find the horizontal asymptote. Either it's bigger on the bottom, in which case 0 or y equals 0 would be our horizontal asymptote, or another case it could be bigger on the top, in which case there is no horizontal asymptote. There might be something called a slant asymptote, but we know for sure there is no horizontal asymptote. Another case could be that the exponents are the same, so we will have to divide the coefficients of our leading term. So if we can remember these 3 cases with the acronym Bobo-Botten eats DC, then we will always be able to find a horizontal asymptote. And again, I know we have the idea already, but I just want to make it absolutely clear what we mean. So when you look at our rational function, look at the leading terms. If it's bigger on the bottom, for example, let's say we had the rational function x plus 1 over x squared plus 3. Notice the power here is 1, the power here is 2, so it's bigger on the bottom, so we know for sure y equals 0 is our horizontal asymptote. we had the other way around, x squared plus 3 over x plus 1, this time it's bigger on top for our leading term. So we know that there is no horizontal asymptote. And if the exponents are the same as if we had x to the fifth, let's say we had 2x to the fifth plus 3 over 7x to the fifth minus 8. We know in the leading terms, we both have a power of 5 in the numerator and denominator, so we would have to divide, since the exponents are the same, we would have to divide the leading coefficients, and we would end up with y equals 2 over 7 for our horizontal asymptote.